on the following facts: that if you are given a vector field that is a gradient, there is a scalar function f whose gradient gives our vector field. We have these three properties for it. First of all, the integral of f along the path does not depend on the endpoints. Indeed, we know that the value is f at the one end minus f at the starting end, which was called the fundamental theorem. We saw that in general, not just for gradient vector fields, but also for any vector field, these two conditions are equivalent. We have independence on the path if and only if integral is 0 over all closed curves. I showed a sketch of the proof of this. The third condition is that for such vector fields, partial of p with respect to y is equal to partial of q with respect to x. The reason being that both of them equal partial fx. Actually, one of them equals partial fyx and the other equals partial xy, but we know that if you have continuous second derivatives, these are always equal. Now, the question is, if you look at a vector field and some of these properties hold, say property 1 holds, does that mean you can find a scalar function so that gradient is equal to f? So if you look at a vector field and one of these conditions hold, does it mean f can be written this way? It turns out the property 1 and 2, because they are equivalent, are pretty strong. So if you have a vector field that satisfies condition 1 or satisfies condition 2, then such little f does exist. So let's write this very important fact down. So theorem: if condition 1 or equivalently condition 2 holds for some vector field f, then for sure there exists some f of xy such that this f we started with is indeed gradient of that. So every vector field satisfying condition 1 or 2, if we test every closed curve and the integral is 0, then definitely there is some real valued function whose gradient provides us with the vector f. So it shows that condition 1 equivalent to 2 is very strong. Condition 3 is not as strong, and this is quite interesting. I was thinking about it myself. So you have some open set. It can be pretty complicated. When you look at condition 1 and 2, it doesn't say if you're looking at curves that are short or long. So it's very global condition. You can go all the way, travel throughout your region and come back. And condition 1, assuming that a function satisfies this, a vector field, is pretty strong. It's true for both very small curves, also for very long curves. That's why condition 1 and 2 are very strong. But condition 3 is a pointwise condition. You take derivative, which always involves very tiny local data, and you're requiring some sort of equality. That's where condition 3 is a bit weaker. You only locally know something is true, but you cannot often for free guarantee global conditions. That's why we have this other fact. These are really deep mathematics, to be honest. They involve some topology and stuff. So fact is that if f satisfies condition 3, but not 1 or 2, then it may be true that f cannot be written as gradient of some function for any f. So for arbitrary regions, this actually fails, and there are easy counterexamples to show that. What is true is that if we are looking at a very small subclass of open sets, and that gives us this simply connected condition. So let me state the theorem and then explain pictorially, as the book does, what these simply connected regions are. So if D is a simply connected, this is a technical mathematical term, it is indeed in topology, it's even beyond calculus and analysis, is a simply connected region in plane, and f given by pi plus qj satisfies that partial of p with respect to y equals partial of q with respect to x at all points in D, then f is conservative. There exists scalar valued fxy such that our vector field f is gradient of that little f. So for certain domains, condition 3 also becomes sufficient to guarantee that this can be solved for little f. So what are simply connected regions? So the counterexample, the kind of spaces where claim fails are those with a hole. For example, if you remove just one point, for example the origin, if you look at all of R2 minus the origin, then you can indeed construct a vector field where these partials are equal, but then vector f does not come from any gradient. And you can have a closed loop going around the origin, and for that vector field you can indeed have this not zero despite that being a closed curve. Remember that condition 1 was sufficient, so if every closed curve integral was 0, we would have a solution to that. So that means for some closed curves this integral will not be 0. And it turns out that this can happen only if this closed curve that you take contains some hole, something outside the region. And that therefore at that point you don't owe this function anything. The condition holds only in the region, not outside. So if there are some outside points inside this curve, then this condition provides no restriction on behavior of the vector field. So vector field can do anything around this point because it's not technically in the set D. So that's the whole idea. So if you have a region where closed curves might pick up points from outside the region, you may be in trouble. A simply connected set is one where this never happens. There are no holes in your set, not even a single point missing, as that in this case proves important. So let me draw some pictures of not simply connected domains. Usually people draw a grass golf course with a lake in the middle. So if you have this green region, it's not simply connected, because if you take some closed loop, say here, you see that its interior contains some stuff from outside the open set. On the other hand, if you take so this is not simply connected. If you take, say, something like an oval with the inside, okay, it doesn't even contain the outside, but this is simply connected. If you take any loop, there are no missing points in the inside. Another way of looking at it is that you can shrink continuously this curve to just one point. You can collapse it to nothing within the region. Here you cannot collapse it to nothing because you can never avoid this empty part in the middle. Of course, this doesn't include such things because this curve is not even in the region. So you're not looking at such closed curves. The condition of simply connectedness is that if you take a loop within that open set, it doesn't miss any point, or it doesn't pick any point from the exterior of the set. Again, these are delicate topological considerations. All you need to know is that for not so bad domains where points are not missing from the interior, equality of these partials for a vector field is again a sufficient guarantee that it can be written this way. So for simply connected domains, either of these conditions 1 and 2 and 3 are equivalent to vector field f being of the form gradient scalar f. I want to end this here. So far it's all abstract and theoretical. In next lecture, I will show you that once we know a vector field can be written this way, how do we actually find it? How do we find f if after we know such f does exist by abstract theorems? We'll talk about it in detail later.